Before we take a deeper dive into polynomials, we're going to pause and do a throwback to quadratics. Quadratics are polynomials. They're a certain type of polynomial. But I just want to jog our memory so that as we move into more depth with polynomials, we can bank a little bit on our prior knowledge with quadratics. Quadratics specifically are a polynomial function where the degree of the polynomial is 2. So if I were to graph a basic quadratic function, we would likely graph f of x equals x squared, which is just this nice upward facing parabola shape. So the graph of a quadratic creates a parabola. And there's a unique characteristic of quadratics, special to quadratics, and that's something called the vertex. And what do you remember so far about the vertex of a parabola? What seems to stand out about this graph compared to other graphs that we've seen before? And you're probably indicating, well, it's this point right here, right? And in this graph, right, the one that I just drew, this vertex happens to be the lowest point ever touched by the function. If I simply turn that parabola shape upside down though, right, just notice the vertex could as well be the highest point ever touched. So a vertex is going to be either the lowest or the highest, depending upon whether the parabola opens up or down. And as we learned in the last video, that's tied to the value of the leading coefficient. So the reason I wanted to do this video is not just to look at the base graph, but to talk a little bit about transforming quadratics, which we have already, so we'll bring it up as something that has been discussed. And then we'll use that knowledge to consider finding the vertex of a quadratic function when it's not written in a particular form. So that sounds like a lot. So let's go ahead and dive right in. So what I'm going to start by doing is writing a function that looks quadratic, but I'm going to insert h, and k. And you're probably recognizing a, h, and k from when we studied together transformations of functions. We have a little bit of knowledge about what a, h, and k do. So just to validate what I know you're all thinking, what does a do again? A actually is pretty powerful. A can be related to, does the graph reflect, right? Does it go beneath the x-axis? That's one possibility. The other thing A could do would be that A could make the graph narrower, or A could make the graph wider, depending upon its value. So you probably remember that. What about H? What does this H value do? H causes what type of transformation? So H causes horizontal transformation. It means the graph literally would pick up and move left or right. It's a little bit counterintuitive because if you do something like +2 for the value of H, that actually shifts it left by 2. And then if you do a value like -3, that would actually shift it right by 3. So H is tied to the left-right motion of the function. And that means for K, you guys are all right with K being the vertical shifter, right? So this is going to throw your graph up by K units or perhaps down by K units. So K controls the vertical shifting. A positive K sends the graph up, a negative K sends the graph down. Cool. So the reason I bring all that up is it turns out that this vertex characteristic that I'm bringing up again as something that's important specifically for quadratics can actually be found just by knowledge of transformations. So if you're given a quadratic that looks like a parentheses x minus h quantity squared plus k, the vertex is at h comma k, which is pretty cool. So if it's given in this handy form here, we can pick off the vertex values just from that form, which again is really, really neat. So what I'm going to do is give an example where it's not given in this handy form, which means we're going to have to do some algebra to get it in that form. Once we have it in that form, we'll just state the vertex and that'll be about all there is to it. So probably something you've done before, just if anything, a little refresher before we dive into higher degreed polynomials. All right, so I do have one ready, which I accidentally showed a moment ago, so you may have already seen it. We're going to try writing the quadratic function, f of x equals x squared minus 6x plus 2 in vertex form. So what that means is we want it to look like that form I had written on the last page, which involved x minus h quantity squared plus k. Alrighty, so this is probably one of the hardest things we've done so far. It's a process called completing the square. So we are going to use completing the square to make that happen. And we'll walk through the steps of completing the square as if it's been a little while since you've done them. So taking the original function we're given, what I'm going to start by doing is leaving a little bit of space to add a particular value. And then I'm also going to leave a space to subtract whatever that same particular value is. So what we're doing is we're rewriting a function. It needs to be equivalent. So if I need to add a certain number onto the function, I'm allowed to do that only if I similarly subtract off that same amount. So it's like we're adding 0, right? If I add, I don't know, 7 and then subtract 7, I haven't changed anything about the function. And that's kind of the trick of completing the square. So this is going to create an easy pathway towards this vertex form sitting at the bottom here. So this is our goal, and I'll have to erase this in just a moment to make room, but this is what we're trying to make our function look like. So to remind you on completing the square says if you add the right value here, it will cause these three terms to be a perfect square trinomial, meaning that it factors as something times itself. All right, and that's a mouthful, so we'll do it bit by bit here. There is a little formula for completing the square, which is you take the coefficient on x, you divide it by 2, and you square it. So in this problem, the value or the coefficient on x is -6. So if I take -6 and I divide it by 2, that'll give me -3. And then when I square -3, I'll get 9. So in this problem, 9 is the value that will complete the square on the first 3 terms in this function. Because 9 is what I need to do that operation of completing the square, just make sure you also subtract 9 at the end so that we haven't in any way changed the value of the function. We just had a fancy way to add 0. Plus 9 minus 9 is a fancy way to add 0. Okay, so I'm going to continue working this down. Our next step is by adding 9, we may or may not have realized that we just made it so that this trinomial here factors. So factoring is something you've learned in previous algebra classes, but basically to get an x squared, I know I times x by x. And then I need two numbers that multiply to +9 while adding to -6. And if you think through ways to multiply to +9, you have a couple options, but I don't think it'll take too long to realize that if you use -3 times -3, the product of -3 and -3 is +9, and the sum is -6. So that's starting to look better. At the end of the function, 2 minus 9 sounds like a -7, so just combining like terms there. Okay. So we are so close to that vertex form. I am going to go ahead and back this out for a moment so that I can finish the process in a less cramped environment. But all I'm going to do for this next and last step is remind myself that if I have x minus 3 times x minus 3, I can write it as x minus 3 quantity squared. So now I can see the value of h, I can see the value of k. That means I can identify the vertex. So the goal was to write it in vertex form, so technically that's done. And then I'm just going to back out a little bit and say, okay, then what's the vertex based on that final function? So the vertex will be located based on our shift. So notice this -3 indicates I shifted right by 3 units. So that means the x-coordinate of the vertex is +3, because a -3 as the h value actually means we shifted right by 3. And then the -7 means we shifted down by 7, so the y-coordinate of the vertex is -7. I'll leave it to you to graph this in Desmos to verify that 3, -7 will be the vertex of that graph. So if you were to graph it, it would be, in this case, the lowest point on that parabola, which is pretty cool. So hopefully that process feels a little bit familiar to you. If it's new, that's okay too. And we'll go ahead and call it right there for this one. Our next videos will move more into broader polynomials.